Thank you for coming. Today, I want to talk about in-situ aircraft research for cloud research. And today, I want to talk about why we need blue waters for this research. Of course, blue water is not on board. It's too heavy, heavier than 50 pounds. And I'll tell you why. Okay, first, the sun is our only energy source, and sunlight interact with cloud, and there is a lot of phenomena happen. So to better understand of our climate system, we should know about this cloud radiative properties. Cloud radiative property is determined by concentration and size and shapes of cloud particles. High cold cloud has the non-spherical ice crystals, and low warm cloud has spherical cloud droplet. And in mixed phase cloud, these non-spherical ice crystals and liquid water droplet coexist. So we are using aircraft to measure these cloud particles. I will tell you some background. Okay, so first one is size distribution. Size distribution is a measured number of particles per given sample volume and bin size. And this size distribution is very fundamental for numerical models and satellite retrieval algorithms. Then we are measuring this size distribution using the cloud probe installed on aircraft. Okay, so cloud particles approximately larger than 50 micrometer, we are using optical array probes to measure their size and shapes. However, for small particles smaller than 50 micrometer, their concentration is quite large, and then their size is too small. And then we are using forward scattering probes. And there are several types of different forward scattering probes. And today, I want to talk about these forward scattering probes. Forward scattering probes measure scattered light in certain directions. For example, in forward scattering directions or backward scattering directions, or sometimes both. When particle passes a sample volume, it shines laser beam, and we measure this scattered light in forward direction or backward direction. And we convert this intensity of scattered light to cloud particle size using some assumptions of spherical shape and known refractive index of particles. And there are several different types of forward scattering probe. However, their working principles are almost the same. Let's see, this one is the working principle of a forward scattering probe. So what really forward scattering probe measure is the scattering cross-section. So from measured scattering cross-section, we are using conversion table and get particle size. And then for this conversion table is pre-calculated one, and then we are using the mean theory with assumptions of spherical particles. Okay, so this one is the graph of conversion tables and the conversion table of spherical shapes. Red line is the assuming ice, and blue line is assuming liquid. And left panel is forward scattering direction, and right panel is backward scattering direction. Okay, for a given one measurement, single measurement of this scattering cross-section, there are multiple solutions of particle size are possible. It is mainly due to these oscillations, and this is known problem of due to the spherical shapes, and their error is estimated by less than 50% error. And the next question is, what about such errors in non-spherical particles? Ice crystals in natural cloud can have a spherical shape for very rare cases, but most cases their shapes are non-spherical shapes. It is because the hexagonal shapes are very fundamental, because the is hexagonal lattice structure of water molecules. And some cloud chamber experiment from IDA chamber experiment, 6% of hexagon, 6% of ice crystal just newly formed had hexagonal shapes. And this one is one example, examples of shapes of rare ice crystals. And another lab experiment shows the shape change just after freezing. So this figure shows the liquid cloud droplet. As time goes by, their shape changed to hexagonal column shapes. There are very, very few studies to estimate the uncertainty of these non-spherical shapes on fold scattering probe measurement. However, their estimation is based on T-matrix calculations and assuming axial symmetric cylinder and spheroid here. Of course, such shapes are not real shapes of natural ice crystals. So we have to quantify this impact of non-sphericity of natural ice crystals on fold scattering probes using realistic shapes. So hexagonal column is their shape is defined by length and width, and their ratio is called aspect ratio. So we selected 6 different aspect ratios from thin plate to long columns. And then for the scattering calculation, that means that to solve Maxwell's equation, we use the Amsterdam discrete dipole approximations. Here is the example of hexagonal ice crystal consists of dipoles, and this one is zoomed one, and here. So each dipole or couple groups of dipoles is assigned to cores of blue waters. Okay, let me show you our accomplishment we have made so far. Okay, this figure shows the average error due to non-spherical shapes of ice crystals. If this blue dot is average error for given size, and red dots are maximum and minimum errors when there are multiple solutions are possible. Okay, for this 2 figure is for specific shapes of ice crystal, hexagonal shapes of aspect ratio of 4. Then across the average error across the all sizes is about 41% in forward scattering direction and 53% in backward directions. And these errors can be much larger for other aspect ratio or specific size of ice crystals, and it can be up to 72% in forward scattering and 150% in backward scattering. And then this uncertainty increases with non-sphericity, and such errors are larger than what people did with the T-matrix method, assuming spheroid or cylindrical shapes. Okay. Then we published a paper this year. Okay, so this is new steps, and now we are dealing with non-spherical shapes. So that means that it has lots of different orientations. Like a sphere has just one orientations, and in forward scattering probes, ice crystals or particles are ice crystals measurement made within less than 1 microsecond. So it's very tiny moment. So in that moment, there should be ice crystal have a certain orientation, and corresponding radiative scattering properties are different. This figure shows that 10,000 different orientations of ice crystals and their scattering phase function. So different color indicate each orientation. And this thick black line is orientation average. That is what we are used to calculate these figures. Here, gray shaded area is the forward and backward scattering probes, where forward scattering probes are working. And there is a large variability. By the way, this one is log scale. So there is a large variability, and we are dealing with these variations. Different orientation of ice crystal cause different scattering properties. This is calculate the extinction efficiency of hexagonal column, and different these dots are correspond to different orientation. So we use that 10,000 different combinations of beta and gamma Euler angle to represent the particles' orientations. This is a little bit quite expensive calculations. For example, to simulate the 1,000 different orientation of just one particles, we need 1.26 million node hours, and then each orientation have different scattering properties and also different runtime. So it is really hard to get Bluewater's discount. Okay, anyways, so we did this calculation during last couple years. We have made more than 100 particles calculations, and such this error due to particle orientations of non-spherical particles are much larger than what I showed before. I mean, for orientation averaged one, and it could be more than 500% in forward direction and almost 800% in backward directions. And we should consider these errors in forward scattering probe measurement. And I want to emphasize that every cloud research aircraft has at least one forward scattering probes, and some of them has like more than 2. And so this one is quite important for this cloud measurement. Okay, this is my summary. So I showed that there is a large error in forward scattering probe measurement when we consider orientation average. However, when we go further, when we consider like orientations of non-spherical ice crystal, such errors can be much larger. And that means that we need new conversion tables. This conversion table was built in 70s, and there is no improvement more than 40 years, and we have to make that. And so now I am building new conversion tables, and I'm also using so polarization properties of these particles. to distinguish the dynamical phase of each particles and their sizes. Here, for example, the same size hexagonal column and ellipsoid, they showed totally different linear depolarization ratios. Okay, I'm gonna stop here and taking questions. Thank you.